The goal and purpose of our project was to develop an automated system to deliver and sort objects. The main components of this project are a sorting station, a rover, a robotic arm mounted on the rover, as well as a camera and sensor system also mounted on top of the rover. Next, we will go ahead and do a demo. Because we cannot meet in person for this demo, I'll just have to cut and paste the video clips together. First off, the sorting station sends to the MQTT server which type of object it would like to receive. Next, the rover, working with the camera, try to locate this object on the playing field. Once the rover is in range of the object, the arm goes ahead and picks up the object and holds it. Then, the rover, working with the camera, tries to locate the sorting station and move to the drop zone. Once in range of the drop zone, the arm will drop the object off at the drop zone. Now, the sorting station will pick up the object and, based off of what color it is, place it in its respective bin. Now, the sorting station tells the rover which object to get next, and the cycle repeats itself indefinitely. So now, each of our team members will go ahead and talk about their design and how they went ahead and did it. First, two terms have to be defined. The first one is FreeRTOS. FreeRTOS is a real-time operating system which is meant to be small enough to run on microcontrollers such as the ones that we are using in this course. And what this OS allows us to do is to create multiple threads, also called tasks, which can run with the illusion of running in parallel. And this allows us to have many complex things happening at the same time. For example, we have a thread that handles the communication between our microcontrollers, and another thread that reads from sensors or controls servo motors. The next term to be defined is MQTT. MQTT is a message brokering service. Think of it like the post office. There is a central server running on a Raspberry Pi that each of our microcontrollers are connected to. This messaging service has multiple channels, and any of us can subscribe to any of these channels that we need to. And anytime someone sends a message to one of these channels, anyone that is subscribed to that channel will receive the message. And that is pretty much how we determine who needs to get what information and how you send that information to one another.
So now go over the constraints of the OpenMV along with the reliability and robustness of the camera and the system. So first and foremost, we'll talk about searching for objects in the real world. These are not going to fit the same ideal conditions of the lab with a specific table color. It is going to grab the camera itself other colors besides the target object of those hues of red, green, and yellow. The field of view of the camera is another limiting factor based on its orientation, either horizontally or vertically mounted. Its degree field of view is going to change. That also includes its ability to grab April tags and other things, because April tags require a lot of computation for the OpenMV, so that's going to restrict its resolution further. And like I said, the floor color also will affect this. The battery life of the battery charging or powering the OpenMV and the TI board is a considering factor. If a battery of sustainable amount is provided, the cam and the battery, and the TI board will have the ability to run for days at a time. The hardware of the camera also is set up in a way that upon failure, it instantly restarts the program and begins running again as well. So now we'll go over to the system diagram, just briefly discuss a little bit how the system all works together. So we have here in the beginning, the camera read task is basically the driving task of this program. Here it's going to receive messages from MQTT, and they will be put directly into the camera read queue by the MQTT task. These messages will be deciphered by the camera read task based on the color of the object, or whether we're looking for the station or an object of a particular color, and that will then adjust the camera read task to then spit information back into UART to the cam itself. That will then adjust the parameters of what the object is and return new parameters for where the object is located or if the object is found. This information is all then transferred and packaged up back over MQTT and sent through the MQTT task, and then able to be subscribed by other objects in the system.
The sorting station coordinates between an arm and a camera to pick up objects placed in front of it and sort them into their correct location. The camera is in charge of detecting and locating objects placed in front of the station. Its algorithm combines results from color space transforms, blob detection, and geometrical calculations to determine the distance, angle, and classification of objects placed in front of it. On a set interval, it then sends this data to the TI board through a UART interface. The arm is the primary actuator in the system, responsible for sorting the components. Controlled through UART, the arm operates off of a lookup table, indexed with the positional data sent by the camera to collect and sort detected objects. The arm and the camera are coordinated with an FSM. Guiding the system through several states, the FSM helps to ensure that the behavior of the system will be reliable and predictable. The constraints for the system dealt with cost, communication, and classification. Our ARM had to be less than $100, which we met with a slim margin. Its components needed to be able to communicate with the board, and since both components use UART, this was able to be achieved. Lastly, the camera algorithm needed to recognize 3 classes of objects, which it does successfully. The behavior of the sorting station is reliable as long as the camera continues to send accurate measurements. However, due to factors such as lens distortion and differences in lighting, the camera sometimes only detects part of an object, leading to rippling inaccuracies in its further positional calculations. These inaccuracies lead the arm to try to pick up objects that sometimes aren't there, or the arm might stall when it tries to pick up that object. In future iterations, this can be amended by adding additional sensors to the system, such as a distance sensor. Lastly, the robustness of the sorting station relies heavily on the accuracy of the camera. As previously stated, there are a variety of factors that affect this, and further tuning and iteration still needs to be done. The system performs well under controlled scenarios. However, it does begin to falter in environments with poor lighting and visually noisy surroundings. But, overall, sorting station accomplishes what it set out to do: sort objects.
Hi, I'm Alex, and I will present my work on this project. Pictured here is my code structure. There are 3 main tasks that I created to control the arm. The first one is the MQTT task, and this task receives messages from the other components on the server, such as the distance and angle of the object that I need to pick up. The next task is a finite state machine task that uses messages from the server to determine what action needs to be completed, such as pick up, hold, or drop off. The final task is the arm control task, which controls the servo motors on the arm via PWM and a timer for smooth movement. The FSM task sends the arm control task which position the arm should move to, and the arm control task converts distance and angle to PWM values to send to the motors. These 3 tasks, which communicate to each other via cues, is what allows for my arm to do what is required. Now I will talk about the constraints, reliability, and robustness of my design. The constraints of my arm are the physical mechanics of it. I can only grab objects that are 8 to 13 centimeters away, and also can only drop off objects that are within 8 to 13 centimeters away, and also these ranges have to be within 0 to 180 degrees from the left side of the arm. That is, my arm can go left and right, a total of 180 degrees. Also, the arm cannot lower itself completely to the ground, so any objects that need to be picked up must be within this region and mounted on some sort of pedestal so that it can be reached. The objects also need to be very light, as the motors on the arm are not very strong. The reliability of my arm is very good. I use lookup tables with a high degree of precision to calculate distance and angle. If the object's position is reported correctly, my arm will certainly be able to move to that position every time without fail, and with a reasonable margin of error, about 1 or 2 centimeters max. The robustness of the arm is questionable. If the object is too high or too low from the ground level, then the arm will not be able to pick it up. Also, if the object's position is not reported correctly, then the arm will not be able to work as intended. Future work to amend this would be to place an IR sensor on the claws of the arm and have the arm verify the position of the object with the sensor. That way, if the object's position is reported to be slightly off, the arm can go ahead and verify with the IR first before picking up to make sure it is in the correct position.